All right, so this is again what we did yesterday. So when we were drawing an ionic bond, a couple things that I mentioned in yesterday's video, if you still need to catch up, is that we're going to be using this side of the periodic table today, the one with the charges on it. So you want to make sure that you've located that. But when we draw ionic bonds, let's just review for those who watched it. An ionic bond happens because what needs to happen to those electrons between two atoms? Dylan.
The one with the most valence electrons takes a electron from one with the least, because normally one with the one with the most needs one, and the one with the least needs to lose one.
Yeah, good. That's exactly right. Okay, so we have one of them, which is going to be our cation. The cations are on the left side of the periodic table. So again, there are metals here. These cations, they lose their electrons. So it gives an electron away. It transfers an electron to our anions, which are these nonmetals over here. And so when that happens, then you get a positive and a negative atom. So because you have positive and negative, what's holding those two atoms together? What did you say? Yes, the ionic bond itself is holding it together, and it comes from that differential in charges. So we have positive, negative. They're stuck together because they're attracted to one another because of their charges. Are we with us on what is happening? So when we draw this, we need to show the transfer of electrons from one to another. So if I have sodium oxide, we start by drawing the electron dot structures of sodium. So sodium is, how many valence electrons does sodium have? One, good. So I'm going to draw that guy there. Oxygen, which is oxide, but as a anion, how many valence electrons does oxygen have? 6, good. So we are drawing our electron dot structures there. Now, so one of these, which is sodium, that's our cation, is going to give electrons away. What's that question?
So is there a specific way you need to do the dot structure, or can you do it like 1, 2, 3, 4, or does it have to be?
No, you can go in either direction.
Okay.
That's fine. You just don't want, the way I would know that you did it wrong is if this one was paired up with this guy. Okay. You want to make sure you put one on each side and then come back around. But it doesn't matter what side you start on. It doesn't matter which direction. So you're fine. So here I have sodium with one extra electron, and it wants to give it away over here to oxygen. And by doing that, it now has a noble gas configuration of neon. So that's why I like to do that. The oxygen still needs one more electron. And so what I said yesterday is don't think this is such a small scale. This is a large scale thing where I have grams of sodium and oxygen and combining them. There's millions of atoms around these, okay? I know we're drawing a very small scale picture, but imagine that this is real life, okay? So what's going to happen to make sure that oxygen has its other electron? Another sodium is going to be floating around nearby, and it will also give that extra electron there to oxygen, okay? So then what we need to do is show our crystal lattice that's forming. Remember that positive and negatives don't want to be side by side. So which one of these atoms is going to go in the center? Oxygen will go in the center, good, because it's going to have a different charge. So what we do is we use brackets to say what the atom is. We're going to give it a positive there by writing it like that and saying this entire atom has a 1 plus charge. And it has a 1 plus because it lost one electron. And then you have oxygen. Oxygen now has what kind of charge? Negative 2, good, because it gained 2. And then sodium, again, we have 2 of them, and this one has a plus 1 charge. Okay? Now also be aware that you have a 3-dimensional structure. We're drawing a crystal lattice, which will eventually be a bunch of them going down, up. It would come out of the paper at you. It would be going behind the paper. Realistically, this is a crystal. So if you had a third one, like on the examples yesterday, you had aluminum chloride. The other place you can put that additional one, if you have like aluminum chloride, should have ended up looking like. I know that this is not this problem here, but I just wanted to make sure. Okay. And then you could use underneath it, or you could have gone above it.
Okay.
Does that help for those who did that yesterday? It was the last problem, I think, on the example. Okay, do we have any questions about this? All right, perfect. So what we will do, we're going to name and formula write these today. Okay, so what we're going to do, we see here in this formula unit, how many sodiums are there? Two. So yesterday we kind of extended it by writing that there are 2 sodiums. That subscript tells us there are 2 atoms. And then oxygen, there's only 1. So we're just going to do this process of formula writing today for all these ionic bonds. But I'm going to give you like more concrete instructions to do it so you don't have to draw them out every time. Yeah.
Is there a specific reason sodium is before oxygen?
There is, because when we formula write or name, we always put the cation first.
Okay.
So metals will always go first, or cations if we ever use ammonia. But we're going to do like those polyatomics tomorrow, which you guys don't even know what that means yet, so it doesn't matter. So, yes, Kristen?
So when you're doing all of that, like the point is you have to cancel the plus and the minus.
That's exactly right, and that's what we'll talk about today. So you already know. Okay, so I'm gonna go ahead and hand out your notes to you, and then I'll get my screen changed. For these notes, we're just doing the front page today, but on the back, that's what you'll use for tomorrow. If I have a moment today, I'll print out your work for tomorrow and make sure I get that to you. You're welcome. If you haven't already done so, just a friendly reminder, if you want the extra points for your cell phones, make sure that they're up there. Just throwing that out there, so if you've forgotten. All right. Okay, so I'm gonna leave my screen like this. If you have any issues, like in the back scene, let me know. Can you see all the writing fine on there with it all being? No. Okay. Because I'm gonna have to change the screen here in a second. For some reason, every time I try to enlarge it, it like freezes on me right now. Something happened to the Wi-Fi or break. Yeah, can you move up a desk and see if that helps? Okay, so again, we are going to be talking about how we formula write and how we name these ionic compounds today. We follow a very specific, what we call it is nomenclature, because nomen is Latin for name. So a naming system that tells us how we have to do that. And the reason why we do that is because chemists around the world, no matter what country they're from, we need to be able to communicate, like if I take this and react it with this, then I get this. And everybody has an understanding of what that is. So that's why we use this naming system in order to do that. Do we have this written down? We're good. All right, so what a formula unit is normally what we kind of refer to for ionic compounds in regards to, like, you like to say a molecule for all the things, but a molecule is actually only pertaining to covalent bonds, which we'll get to by the end of the week. But for ionic bonds, we call that simplest unit a formula unit, and it's really just like what we saw yesterday, that fundamental unit, that smallest ratio between the two different elements. If I say monatomic ions, then I just mean the atom itself after it has gained or lost electrons. So after lithium loses an electron, it now is a lithium with a +1. That's a monatomic ion because it's by itself. It's not bonded yet to something else. Really, you would see monatomic ions more like when they're dissolved in other substances. So oxidation number, at least in this class, is really going to be the charge of that atom. So that's, again, if you're looking at your green periodic table, do you see how there's a bunch of charges on here? Those are oxidation numbers or charges. Basically what that means is it's the charge of the atom after it gains or loses electrons. I pointed this out to the kids yesterday, but do you see the ones in the middle boxes? Do you see the middle transitional metals? Yes. Do you see how they look different? You look at iron, it looks different because of what reason? Iron is Fe, number 26.
Loses 2 or 3 electrons.
Good. Okay, so there's a 2+ or a 3+ there. And so those transitional metals can have different charges just depending on how many it loses. And that's okay. It just happens with those transitional metals, and it only happens with the ones that have them there. So we have to make note of that today as well.
So what is transitional metal valence electron? Is it like
well, so our valence electrons, you know, we always say there's a max of 8, right?
Yeah.
Those transitional metals are a little bit different because those valence electrons generally only come from s and p orbitals, like their outermost s and p orbitals. Well, the ones in the transitional metals, we would innately think that that outermost area would also include a d, but that's not those bonds. The d ones are not our bonding electrons. So that's why it's like a little bit more unclear, just so you're aware.
But that's never going to come into question.
No. Yeah, no. Okay, so how we write formulas for ionic compounds. We're always going to write the cation first, which is generally what type of element?
Metal.
It is always a metal normally. So we write metals first or cations first. Then we follow it by the anion. We do this in formula writing and naming. We use subscripts, which are numbers that need to be smaller and at the bottom of the number. You are not supposed to write them the same size as the regular letters. These subscripts will tell you the number of ions that you have in that ionic compound. And the whole goal, just as you had said earlier, Tristan, is that the total charge needs to be equal to 0 for the entire compound. So the whole reason why we're doing this is to make sure we balance out our charges there, and that's why those subscripts are there. But we have a shortcut way of doing this. So I'm going to just insert. Okay. All right. All right, we're going to. So we have those examples on your paper we're going to go over together. The first one is magnesium chloride. The first one I'll show you kind of with the longer version, and then I'll show you a shortcut. All right, so if we look at magnesium chloride, I need to look at the charges for each one. So for magnesium, look at your periodic table, the one with the charges on the back. For magnesium, what does it tell you its charge is?
2+.
2+, okay? Chlorine's charge is 1-. And again, you're looking at chloride because it's an ion, 1-. So we need to balance out the charges so the entire thing equals 0. So based on that, how many chlorines would you need to balance this out? You would need 2 chlorines, right?
Yes.
So I end up changing this. I only need 1 magnesium, so I just leave it as is. Yes. Yeah. There's 1 chlorine up there, and I need another one. So total would be 2. Yes.
Yeah.
Oh, I don't know what just happened. Gotta do something.
Oh, you scrolled down.
Did it work? Oh my gosh.
Oh, you zoomed in. How did you do that?
I don't know. It like will pick up on my paper sometimes.
Maybe it was your hair.
It could have been that too. Oh,
I
not.
feel like I'm a lot of people.
Alright, hold on. I'm not going to get this.
So much stuff I do. I can't sit there and it's hard to feel my fingers around like this. Feel something different. Feel something different.
Alright, so we're here. Alright, so back to where we were. We're going to indicate we need to use those subscripts to show how many magnesiums or chlorines I needed. So I have Mg, that just stays normal. If you just have 1, you don't need to write 1. Okay, just like in the math, when you have 1x, you don't really need to write the 1, right? So we don't need to add a subscript for 1. But for chlorine, I'm going to put 2 here at the bottom of the number as a subscript to say that I needed 2 total chlorines to balance this out. So the entire thing should be balanced and good. Yeah. Now I'm going to show you a shortcut though, because this is like long version. There's an easier way to do this. So the second example just kind of shows you, I actually don't even get to use that shortcut for that one. All right, so if we have magnesium oxide, I have magnesium charge, we already know is 2+. Oxygen's charge is 2-, good. So do I need to do anything to balance these out?
No.
No, they're already balanced, so I just have to rewrite them, okay? So I just write this as MgO, because I only needed 1 of each on that one. Good, that's a good thing. All right, so for sodium chloride, sodium charges
+1.
+1,
Or 1+.
and then chlorine charges 1-. Again, do I need to do anything to balance?
No.
No, so I just rewrite as NaCl. I believe on the next one is where I can show you your shortcut. All right, magnesium we've already been using is a 2+. What is nitride and nitrogen?
3-.
3-, okay? So our shortcut here is the easier way to find, like to write the formula is called the crisscross method or the drop and swap method. Essentially what you're going to do is you're going to take your charges here and you will crisscross them and bring them down as subscripts. So 3 gets brought down here and the 2 gets brought down here. But do not bring the charge down. Okay, so do you see before, these subscripts are just telling you number of atoms. We're going to have a minus and a plus. So when I rewrite this, that 3 now becomes magnesium subscript, and nitrogen has a subscript of 2. So it's a shortcut, so you don't have to think about it.
So all you have to do is.
Yep.
And write it.
Yeah.
So,
Oh my lord.
yes. Parker, that's what I needed.
I needed something.
Because 3, because of.
My day's so much happier.
Well, I'm glad that we're like super pumped right now.
Gold is 80.
All right.
Oh.
This is
Alden, I need you to get like a. Alden, I need you to get an Apple Watch so you can spit.
I need it. Wait, I can't listen. I can't listen. For some reason, when I'm not on my phone, it decides to do like entertainment, smoke on water. But then when I'm on my phone, it knows. It knows.
It knows. It knows. Okay, so now take a look at gold on your charge periodic table. Do you see gold is AU, by the way? What's weird about gold as compared to the rest of the ones we've been doing? It has 2 different charges. Gold can be a 1+ ion or a 3+. So what do you think that this Roman numeral is telling you?
3.
That is the 3+, okay? Our Roman numerals tells us for those transitional metals which one it is. So gold here is a 3+, and then chlorine we already know is a 1-. We crisscross our charges. Again, you don't have to write the 1, okay? It's understood. So we don't need to write the 1 for gold. And then chlorine then will have a 3 that goes after it. Make sure that your subscripts are small though. Piece of cake. All right. And then our last example for this, and then we're going to talk about naming, which basically we're just going to do the reverse of what we've been doing. We have copper 2 oxide. So again, that 2 tells us that copper's charge in this instance is a 2+. Okay. Oxygen has a 2-. So we don't have to crisscross this time because they've canceled each other out. So now we have just CuO as our answer. All right. Do we have any questions about that stuff? No, we're good. All right. Okay, moving on to naming, and then you guys are practicing the rest of the time. So, all right, polyatomic ions. So go ahead and write this down. I'm going to show you where we can find them. So let's like break up what this name sounds like. Poly sounds like what? Many. Atomic means atoms. Many atoms that are an ion is what this is telling us, okay? So this is a group of atoms. A group of atoms that together are like a big molecule, but they have a charge over the entire structure. So this is like ammonium. Ammonium is nitrogen bonded to 4 hydrogens, and the entire structure has a +1 charge. Phosphate is phosphorus bonded to 4 oxygens. The entire structure has a 3- charge. That's what a polyatomic ion is. We're going to write these tomorrow, but when we do, you want to make sure that you don't change the subscripts of polyatomic ions. That tells you how many atoms are in the structure. And where you find your polyatomic ion, look again at your charge periodic table. Do you see that box that's in the center?
Yes.
Yes? All of those are our polyatomic ions. Now that's not even all the ones we could have. Those are more just like most frequently used, okay? But that's what we're going to use tomorrow. I'll make sure, do all of you still have your white periodic tables like the copy I gave you? Because it's on the back, just like this. Make sure you have that available for tomorrow's work, okay? All right. Okay, most of these polyatomic ions are what we call oxyanions, and that means they're negatively charged and they have oxygen in them. Again, in science, we are pretty straightforward, so it sounds exactly what it means. But that's, if you look at all of those, majority of them, do you see how they have a negative charge, and they mostly all have oxygens in them, right? Do you see that? There are a couple exceptions there, like cyanide doesn't have an oxygen in it. Let's see, what's another one that use there are also positive polyatomic ions. Really, we just use ammonium the most. All right, so then this screen is going to tell us how we are going to go about naming our ionic compounds, just like it's the reverse of what we just did with formula writing. But naming ionic compounds is fairly easy because it's like the same thing over and over again. For the cation, you always just say the cation's like regular element name, like just how we just said magnesium or sodium or potassium. We don't change the name of that cation. For monatomic ions, the cations use the element name. Again, that's if it is not bonded to something else. For the anions, though, we are going to use the root word, and then we are just going to put IDE at the end. So essentially what you need to know is that the second word in these names will have that IDE ending. If we need to write the name for a transitional metal that has more than one oxidation state, then what we do is we put the parentheses with the Roman numeral after that specific transitional metal. You only need to do this if there is more than one. So don't do it for all the transitional metals. It's only necessary if there's more than one. And then if we have a polyatomic ion, we are just going to say the name of that polyatomic ion. We are not going to change the name and put the IDE there. So we're going to go over some additional examples. Did we get it all written down?
I'm running my left hand. That'd be funny.
I'm going to stop making eye contact with you. So we have 5 examples to get through, and then you guys will be working the rest of the time by yourselves. I mean, not by yourselves, you can ask questions. Fend for yourself. All right, so going on to our examples here. Sorry, I want to get this up. All right. Okay, so the first example is MgO. All right. So if it is not a transitional metal, honestly, this is fairly easy. We just keep the first word the same. So what are we going to say for the first element? Magnesium. And then Jackson was right. So we're just going to say magnesium. The first word is always the same. And then instead of oxygen, we add that IDE ending to the second word, so it will turn into oxide, like that. Okay? Which means you should be able to go ahead and do the next two. What do we think the second one is going to be?
Sodium chloride.
Sodium chloride. Good. We keep that first word the same. And then add the IDE to the anion. All right, when you get with a transitional metal, check to see if it has more than one charge. For zinc, does it have more than one charge? No, so we don't have to write Roman numerals there. We can just still say zinc chloride. And then the next one, though, is FeCl2. So it is iron chloride, but check out iron. Iron's a transitional metal. So, okay, when we do this, there's two ways you can figure this out. If there is a subscript, because we need to figure out if this is iron 2 or iron 3. The way we do that, if there's subscripts, is we do a reverse crisscross. Okay, meaning if there's subscripts here, then I pull this guy up to the top, and I know that originally it was a 2+. Like we did crisscross to get them down, we do reverse to get the charges. Okay, so when we write this for a transitional metal, we say iron 2 and then chloride there. Okay. But if you have something like AuCl, okay? Look at gold on the periodic table. Does it have more than one charge? Yes, it does, right? Do we see that? It can be a 1+ or a 3+, but there are no subscripts. So this is where you have to balance out by just looking at the numbers. In this case, it ends up being a 1+. But remember in our example of like CuO, they were both canceled out because we had a 2+ and a 2-. We can't assume that it's a 1+. We have to balance out charges. So for we always use the anion here. So if it was a 1-, then this means it has to cancel it out. So it had to have been a 1+. Yeah. So we will write gold 1 chloride. Again, don't assume that it was a 1. You have to balance out the charges. All right. Do we have any other questions? So again, the back we're not doing. We're going to do the back tomorrow. We just want to focus on what we call binary ionic compounds today.